So this is going to be section 1.2 of Griffiths' book, Introduction to Quantum Mechanics, third edition. Section 1.2, the title of it is the Statistical Interpretation. Okay. And the purpose here is to talk a little bit more about what is this wave function that we talked about in section 1.1, which depends on position and time, depends just on x here because we are thinking about a system in one dimension for now. Okay, much later in this course, when we talk about the hydrogen atom, we'll finally move to 3 dimensions, but all the way for this beginning, chapter 1, 2, and we'll be only talking about 1 dimension. Okay, but anyway, what did we talk about in section 1.1? Well, we said that very similarly to what we do in classical mechanics. Now, in classical mechanics, we have an equation that comes from Newton's second law, with which we can predict the future of the system. In which way? Let me remove this. If I give you the initial condition, now if I give you the initial position of this particle, using this equation for conservative systems that do not have friction, using this equation, if you solve this equation, you will be able to get the position of the particle at a later time. Okay, so quantum mechanics is similar in the sense that instead now of playing with position, we are going to be playing with the wave function. And the equation that dictates how this wave function changes in time is this equation here, which Schrödinger's equation. So if I give you the wave function at a certain time, you will be able to get it at a later time. How? By solving this equation. And so all the information I said about the system is contained in this function, which is known as the wave function. Okay, so let's talk a little bit more about the wave function. Well, the important thing to notice here is that in this equation, we have the I, now this imaginary number there, which means if you solve this equation, the wave function, okay, this wave function may be complex. Well, there is nothing in the lab, nothing in the measurement that will come out as a complex number. And so this wave function is an abstract entity, is a mathematical quantity. It's part of the formalism of quantum mechanics. It's not something that is physical. It's not something that you're going to be measuring. What is physical is the absolute value of this wave function. Okay, so the absolute value of this wave function will be real. Remember how you compute absolute value of a complex number. So suppose we have this number 3 plus 2i, just as an example. And if you want to compute the absolute value square, just as we are doing here, so the absolute value square you obtain by doing the complex conjugate. So the plus here became minus, the imaginary part changed sign, the complex conjugate multiplied by itself. And if you compute that, you have 3 multiplied by 3, you have 9. Then you have this imaginary number here, 6i. You have this other imaginary number here, minus 6i, but this is going to cancel, right? And the last term, minus 2i multiplied by 2i, since I with I gives us minus, we'll get here plus 4. And so you see that we now have a real number. Okay, so when we look at the absolute value or the absolute value squared, as we are doing here, we get a real number. And now this thing can be physical, is physical. What is this? The absolute value squared of the wave function. What does it give us? It gives us information about probability. Okay, we say that this is the probability to find the particle that we are studying at a certain position x at time t. Okay, so the absolute value square of the wave function gives us the probability to find the particle at position x at time t. The proper way to write that is the following. We do an integral of this absolute value square of the wave function in position in a certain range between A and B. And what does this give us? The probability of finding our particle, the object that we are studying, finding the particle between this position A and B at a certain time t. Okay, so what is physical is the absolute value square of the wave function. It gives us probability. What is the chance, the probability that we are going to find the particle in a certain region in space? So what do we have? Like if we want to make a graph of what we are explaining above. So suppose here in the x I have position, okay? And in the y-axis, I'm going to now plot this real quantity, no? Because it's absolute value square of the wave function. And we have here some distribution, something like that. Okay, so when we write this integral, what are we computing here? Well, we are computing the area between some position A and some position B, correct? We are computing the area under this curve. So this area here is the number that will give us this probability of finding the particle between A and B. Now, this plot that I just made here is at a certain time t. No? So this is going to give us, if we compute this area here, we are going to get the probability of finding the particle between this position A and B at this time t. That's all we can get about this particle. In quantum mechanics is probabilistic, and that's the kind of information that we can get. The probability for finding the particle here and there. Now, this is known as the statistical interpretation, or Born's statistical interpretation. Okay, so this is what we are talking about in the previous section one, that quantum mechanics is intrinsically probabilistic. So this is at a time t. As time passes, this plot can change. So let me make it here. At a later time, I don't know, it can be completely different. Something completely different at a later time. Let's call it T2. What determines how the wave function is going to be changing in time? This the equation, Schrödinger's equation. So the dynamics in quantum mechanics is determined by this equation. This equation tells us how the wave function changes in time. Okay. So this is the Born statistical interpretation. What we say, so let's summarize here. We say that the wave function, this is, as I said, complex, can be complex, is abstract, it's not something that you measure in the lab. We say that this gives us the state of the particle, of the object that we are studying, okay? And as we said, it can be complex. But the absolute value square of this quantity, this is real, and this is give us probability of finding the particle here and there according to these integrals that we can solve. And so if I look at this plot here, what do we see? Well, there is a high probability to find a particle around this region, because we have a large probability. We also have some significant probability to find it here. Well, very low, almost zero probability to find a particle in this region. Okay, but as I said, this changes in time according to the Schrödinger equation. Very well. So quantum mechanics is intrinsically probabilistic. Let's discuss this a little bit more. In that beginning of the course, section 1.1, we will talk much more about it, we mentioned the uncertainty principle. For example, for position and momentum. What did we say there? That we cannot know, now according to the uncertainty principle, which we'll learn more about. According to this uncertainty principle, I cannot know the position and momentum of a particle with absolute certainty. There is some indeterminacy. There is some lack of knowledge in these two things. I cannot know both at the same time with absolute certainty. So this product here, which gives us the uncertainty, between a certainty in these two quantities is larger than some finite value, not non-zero. Okay, but if I make a measurement, so if I measure one of the two, either position or momentum, then I will know that one precisely. Okay, so what do I mean? Suppose at a certain time, let me make my plot again of that absolute value square of the wave function. So at a certain time t, I do not know precisely where this particle is. There is some distribution telling us that we have a good probability to be around here or around there. And this is at a certain time t. So there is an uncertainty. If you compute the variance and if you compute the standard deviation of x, you will get a certain value there. But if you then decide to measure it, you will know exactly. So if I decide to make a measurement of position, the position of this particle, I will know exactly where it is. Let's say I will know after the measurement that the particle is exactly at some position. I'll call it the position A. Well, what does that mean in terms of this plot? Above here, now we had this distribution, probability to find a particle here and there. After the measurement, I said, then I do find that my particle is exactly, let's say, at this position A. What does it mean to this probability, not to this absolute value square of the wave function? It means that it suddenly, now when I make this measure, it collapses. So that's the term. The wave function collapses and to exact this position. So it becomes a delta function at this position. That was what came out from my measurement. Okay, so this is the collapse of the wave function. This kind of interpretation is known as the orthodox interpretation. That says, well, before measuring it, you don't know where it is. There is some wave function that can give you the probability for being here or there, but you do not know where it is. It's only after measuring that you can know with certainty. Okay, now the problem with this view, this is the view that we'll be using. This is an interpretation of quantum mechanics that I'll be using. I'm just going to mention to you here something out of curiosity. If you're interested, you can read more about it, and I can give you references for that. But what is the strange thing here, or for some people, that in this equation, the main equation that describes the dynamics of the system, Schrödinger's equation, you don't have in this equation a description of this collapse. Okay, there is nothing in that equation that describes the measurement. Okay, so this is known as the measurement problem. That this process is not very clear or is not really contained in the theory, the measurement problem. Okay, and this led some people develop other interpretations of quantum mechanics. These other interpretations of quantum mechanics is studied in what is known as foundations of quantum mechanics. Foundations of quantum mechanics is also studied by many philosophers. Okay, so this is not at all the topic of our course, but I'm just telling you this. So interpretation for you to know about these things, that they exist. We will just assume this orthodox interpretation, but there are others as well. There are some realist kinds of interpretation. You may have heard the famous sentence by Einstein, no? God does not play with dice, because Einstein was uncomfortable with this idea of quantum mechanics. No? Einstein or Bell or Bohm are all examples of people who are uncomfortable with these notions of uncertainty in quantum mechanics. For people, for realists, the idea of what they were trying to develop is, well, if at a certain time you measure the particle and you get it exactly at position A, right before it should be very close to this point A. Okay, so while the orthodox interpretation will tell you, oh, it's nowhere before you measure. It may have some probability distribution, but you don't know exactly where it is before the measurement. Okay, well, some people you may have heard say, oh, Einstein was wrong, but these people, I think, this is my opinion, okay? So these people were skeptical, and that's the job of a scientist, to be skeptical. By being skeptical, you will get a better understanding of science. So you should not, if you want to be a good science, don't accept anything as a dogma. It was from these questions that Bell, for example, was asking that he was then able to show he was a realist, and by asking the questions, by being skeptical, he was then able to show that a group of these realist theories known as the hidden variable theories were wrong. They would not predict the physics that we see. And which kind of hidden local variable theories? The local ones. Okay, so by being skeptical, he was then able to show that theories that were being developed in this context of realist position was wrong. The only one that survives in this story, or at least one of those that survive, one of these hidden variables theories that still survive nowadays, is one by Bohm, which is a non-local hidden variable theory. There is another interpretation of quantum mechanics that you may have heard of because it's very popular in movies, for example, which is the many world, or the idea behind of the many world interpretation. Okay, but as I said, these discussions of interpretations is not the topic of this course. I just wanted you to know about it. No? But at least to have heard that they exist in your life. Our point of view here will be of this orthodox interpretation, more associated with Bohr, who discussed a lot with Einstein. And what does it say? Before measuring, you don't know where the particle is. There is some probability distribution, you don't know where it is. Once you measure, you have this collapse of the wave function. How exactly this happens? Well, it's not in the theory, and you may not even want to ask that, but basically that's the idea. Now, after the measurement, okay, after the measurement, so we made a measurement and we found our particle, let's say, right here, at this exact position, which we were calling position A before. Okay, so this was at a certain time t. Right after this, immediately after that, if you measure it immediately after that, you will find it again at position A. Okay, so immediately after you find it there. But if you wait a long time, so longer time, later, it doesn't have to be that long, but later, if you don't measure immediately after, but later, what is going to happen? Well, Schrödinger's equation will play its role, and you can then spread that wave function again. Okay, well, the important summary of this section 1.2. Okay, we talked a little bit about interpretations of quantum mechanics. This is not part of our talk, of our course. What is really important, the absolute value square of the wave function, okay? And the integral of this absolute value square, because this is what is physical. No? This gives us the probability for finding the particle. So as I said, everything is contained in the wave function because this abstract quantity, once we do the absolute value square, we get something that is physical, probability. Quantum mechanics is intrinsically probabilistic.